SwayamPrabha. Digital India. Educated India.
So, hello, welcome back. So, in the last class we have discussed about the mechanics of how basically large scale eddies or the kinetic energy of the large scale is transported across the different scales and finally it is dissipated into the smaller scales. But so far we have restricted our discussion to non-reacting turbulent flows, and we have discussed a few of the things, but now it is time to move on to the basic topic of interest, that is turbulent combustion. Okay. So, the general structure of turbulent flows, you see, when you have turbulence in combustion, it has basically two-way effect. There is like interaction happens in multiple scales through different kinds of things, so convection, through transport, turbulence enhances diffusion, and also it affects the reaction, the mean reaction rate, as you will see later. But to the first order, what it does is that it increases the burning intensity through enhanced mixing and increased flame surface area. Okay, because when you have flame in turbulence, turbulence essentially stretches and folds the flame at a multitude of length and time scales, and the overall area is increased, and when the overall area is increased, the mass flux and if the mass flux per unit area remains nearly constant, then the overall burning flux essentially increases, and as a result of that the turbulent flame speed becomes much greater than the laminar flames. But that is for premix combustion. For non-premix combustion, of course, also turbulence helps in combustion because it essentially helps in mixing. So, turbulence has a positive effect in combustion, but at the same time it can also lead to local extinctions if the stretching due to turbulence is too hard, too strong. So, yes, as you said, that excessive turbulence intensity, that is E prime RMS or URMS, can cause small URMS can cause local extinction also. Now, effects of chemical reaction, when you have heat release, it kind of have as a relaminarizing effect, because the Reynolds number is essentially rho Vd by mu, and to the first order rho by mu has a t to the power of minus 1 plus alpha dependence, whereas if we say that rho depends as 1 by t and mu depends as 2 to the power minus alpha, whereas alpha is greater than 0. So, the Reynolds number essentially decreases when you have combustion, and but at the same time it can, because of the flow acceleration and the large density gradients it creates, it can essentially also supply energy under certain circumstances to sustain the turbulence. One of the mechanisms can be like the baroclinic torque, that which is essentially the cross product of the 1 by density times the pressure gradient, gradient of 1 by rho, that is 1 by density times the gradient of pressure. So, when this density gradient, when density and pressure, the density gradient and pressure gradient are misaligned, then you have this baroclinic torque, which essentially produces vorticity, and also there are other things like flame front instabilities which can also help in turbulence generation. But here the main focus of our discussion on turbulent flows will be essentially towards basically the modeling the turbulent flows, and for non-premix and premix combustion, as we will go later, we will go into different kind of the mechanics of the turbulent flame interaction also. But one of the biggest challenges in turbulence is, or in turbulent combustion, is that how can you use reduced order models to basically describe the turbulent combustion. Of course, if you do not want to use a model, one can use something like direct numerical simulation. We will go to this. One can use direct numerical simulations, where essentially you resolve your simulation from the largest scales to the smallest scales. Of course, the scale separation, as you know, L by eta is essentially proportional to the Reynolds number to the power of 3 by 4th, and hence as the Reynolds number grows, which is very high in practical engines, your scale separation is very large. That means you have to have a very large number of grid points as well as very large number of time steps to basically resolve all your spatial length scales as well as the time scales of the problem, and that creates prohibitively creates a demand for prohibitively expensive computational power. So, practical engines you cannot do DNS on them. Okay. One can do, so basic approach would be to basically do the RANS simulations, that is you basically use the Reynolds average Navier-Stokes equation or Favre average Navier-Stokes equation. You will see what that means. Favre is meant by Favre averaging. You will use some sort of an average Navier-Stokes equation and try to describe the average flow field instead of the instantaneous flow field. But as you will see that this also had some problems, but still in the industry this Reynolds average Navier-Stokes equation or average resolving the average flow field through CFD has been of great interest, and that is widely used in the industry. So, in this class itself we will go into the different how this is done, how to use this kind of like average Navier-Stokes equation and average species equation and average temperature equation, how that can be used for describing the turbulent combustion phenomena as such. And so, in this class in this next 2 hours class we will essentially focus, or this next 2 hours module will essentially focus on this RANS, how we can use RANS or this average Navier-Stokes and average species equation, governing equations, average temperature equations towards basically solution of the flow fields, and then we will move on to the different and then we will move on to the other basically more sophisticated modeling approaches. Okay. So, first we need to introduce a different kind of averaging called Favre averaging, because just if you average the flow field like we did for previously, that is we just take the arithmetic mean of the flow field or what is ensemble averaging, then we will end up in problem in density varying in flows which involves density variation. So, for flows which involves density variation we will introduce a different kind of averaging. But before we go into the different kind of averaging, we just recap what we meant by what was the conventional averaging. So, the conventional averaging was done by done towards Reynolds decomposition, where we took this flow field instantaneous flow field u x t, okay, and then we averaged it in this way, and then this was the mean component and this is a fluctuating component. Of course, the mean of the fluctuating component was 0 and we defined the variance in this manner. Okay, now we introduce a different averaging called Favre averaging. So, what is Favre averaging? Favre averaging means that here we decompose a flow field of a variable density flow, that where density is not essentially constant, it can vary with space and time. So, for those kinds of flows we consider again this velocity at a particular position given by the position vector x vector and time t, and that we decompose as this u tilde plus u double prime. So, where here u tilde is not just, so u tilde here u mean was just averaging over u mean, but here u tilde which is not equal to where u mean is not equal to u tilde, whereas u tilde is defined in this manner, that is it is essentially density weighted averaging, okay, divided by mean of density. Okay. So, this is this thing, and when you do that this is the definition of the fluctuation, that is mean of the density times u prime is averaged when we average that by the conventional averaging, then that average is equal to 0. Okay. So, why do we do this? Okay. The reason is the following, that if you in the momentum equation, so in the, as you know, the turbulence, the heart of turbulence comes from the non-linear term of the momentum equation, that is the second term on the left hand side, right. So, if we do a Favre average, if we do a conventional Reynolds averaging on this non-linear term of the momentum equation, which is essentially this, or the rather it is a gradient of this, but when we do the averaging, because gradients and averaging commutes. So, when we do that we will decompose it into this manner. Okay, we will get this thing when we do a normal ensemble averaging on this term, that is rho times u times v, and we average that, what we get is that average rho times average u times average v, and then of course these terms all these terms we essentially get 1 2 3 4 5 terms. Okay, and none of this goes to 0. Whereas, if you do if you essentially do a Favre averaging, what you will get is this thing. That is, if you do a Favre averaging, if you introduce Favre variables and then you do the average of this same term, what you get is mean rho times u prime v prime plus rho u prime double prime plus v prime. It can be easily shown in this manner, that is in this manner itself. So, we just introduce some white pages, we will need a lot of those in this class, because I will do this mainly these derivations analytically. So, now if we do this consider again this variable, that is this rho times u prime v, times v, okay, that we can write as and that is equal to rho u tilde v tilde plus rho u double tilde v tilde plus rho u tilde v double prime plus rho u double prime v double prime. Okay. Now, if you take average of this, what happens is that, of course, you have averaging on this. This is need not be average, because this is always averaged quantity. Now, when you take average of this thing, when you take average of rho times u prime, u double prime, then it goes up to 0. Similarly, this average of this rho and v double prime, that goes to 0 and this stays. So, the terms that stays is essentially out of the 4 terms, only the 2 terms stays. So, this is the advantage, that is this is the thing that we get, okay. And this is of course this is similar to that Reynolds stress term, but here it is Favre averaged rather than normal Reynolds averaged, and these are just all right. So, now we can use this concept of Favre averaging. So, clearly the Favre averaging of course is advantageous, because it just reduced the number of terms from much more number of terms in this nonlinear term to this only 2 terms. So, essentially the analysis becomes of this Reynolds or this Favre or this Reynolds average Navier-Stokes equation, but with Favre variables it becomes much more simpler. So, we will use this Favre averaging for the rest of this class when we deal with turbulent for the entire class of where we will deal with turbulent combustion. So, this is the averaging of choice that is used in turbulent combustion. Okay. So, next we go back and apply these things in the Navier-Stokes equation, and then we generate the turbulence models. Now, first of all, of course, before we go to the Navier-Stokes equation, we need to go into the continuity equations. So, here we go into the Navier-Stokes equations, and so first is of course the continuity. We cannot just consider divergence of V equal to 0, because now you have got density variation. So, the equation of that we need is this one. this bar is not averaging, this is vector. And then we have the momentum So, in the momentum equation you get this left hand side acceleration term, the temporal acceleration, convective acceleration, which is equal to the minus of the pressure gradient, the forces, plus divergence of the gradient of the strain rate tensor of this gradient of this viscous stress tensor essentially. We neglect gravity. And this needs a closure equation which is given by this. This is the strain rate tensor, whereas the strain rate tensor is given by this is the transpose of the velocity gradient, and mu is the dynamic viscosity here. Okay. Now, if you introduce Favre averaging here on this continuity and the momentum equations, the equation we get are these. So, this becomes this is angular brackets is normal ensemble averaging, it is not Favre averaging, plus this term V vector Favre average, and later we will not actually use the V vector sign. So, without the overbar, this means that the Favre averaging on the V vector itself. Okay. So, this is the Favre averaged continuity equation, and the Favre averaged momentum equation is the following. Normal averaging, gradient of the mean shear stress tensor minus the Reynolds stress terms, but here it takes a different form because of the Favre averaging. So, these are velocity fluctuations, and this is the term. So, this is the Reynolds stress that appears in the Favre average momentum equation. Of course, here also the problem is similar, that is you have an equation, a governing equation of V tilde, but you while you introduce the averaging, you encounter this new unclosed terms which is V prime tilde, and you need to have some kind of a modeling for that, otherwise you cannot solve this equation. Okay. So, these are the concept of Reynolds stresses.